So I think you all understand about the upper bound curve. This is the 1991 upper bound curves, and 2008 Robinson and Puri Pushpinder was working together at Air Products, so that you will be able to listen to in more details about their activities in Air Products in terms of gas separation and energy applications. And then Robinson again plotted this in here, and looks like that we have a few polymers that is over the upper bounds for oxygen and nitrogens. In terms of the CO2 and methane, we have blue spots. These blue spots were recognized as the TL polymers, and we have a very high permeability, and there are several orders of magnitude higher than the traditional polymer membranes. But these were treated at high temperature. These were, at the time, these were treated at 450 degrees C and very close to the carbon membranes. And this is the extreme case where right now we are working on the little lower temperature because of the mechanical strength of the polymers in terms of hollow fibers. And we are working on with a copolymerization system, copolymer system, rather than the traditional TL polymer systems. The third issue is about the stability of the dope solutions. So the monomer at the time should have been changed, should have been replaced by the new monomers. So so I have to note that this is the extreme cases. Anyway, this is the new concept, and right now the TL polymer, the Hanyang University is again the mecca of the TL polymers, and it's well known, and a lot of people know about this. If you think about the published polymers materials for the pump selectivity, usually, in 1994, he noted that there are several polymers of interest to have a high permeability. Okay? If you look at the selectivity, high selectivity, and the permeability of the polymers, it's only in the range of 1 to about less than 10 bara of the oxygen permeability, which is very small. If you look at the oxygen nitrogen, 1 bara to about 10 bara is in this region. The selectivity between the 7 to about 5 is right in here. So these polymers were listed here in this case. Okay? In some cases, you have a pretty high selectivity. In some cases, a little lower, but high permeability. Okay? So, the knowledge, information that we can get from this table is that if you contain the fullerene, what we call it fullerene containing monomer, okay, or 6F, hexafluoro isopropyridine unit containing monomer, then you will be able to get high permeability, okay, high permeability, and reasonable selectivity. Okay? But if you do not have this type of the groups, then you have a pretty high selectivity or a small or lower permeability in this case. So there are always a trade-off relationship. So if you increase the permeability, then you may decrease the selectivity. Okay? Another thing that I have to note is that if you have an ether group here, ether group, this will make the polymer with more flexibility. So you're expecting to have a high permeability, but the result is not, because those flexible group may rearrange to form and fill those cavities, so that actually the density is not decreasing, but rather it increases. So the permeability is not really very interesting in the case of ether containing the monomers. One of the plot that we will be able to look at is excuse me, there is an error. This is 35 degrees C, and this is 25 degrees C. And although you have measured the polymer, two types of polymers in different temperature, but for the same the gas molecules, we have two different trends in permeability over several gases. Okay? The polysulfone has permeability decrease as you increase the size of your gas molecules, whereas for rubbery polymers like a PDMSP, you increase the permeability as you increase the size of your molecules. And this is very typical rubbery polymer behavior, whereas this is the typical glass polymer behaviors. So stiff and rigid polymer like this polysulfone will lower its permeability as you increase the size of your gas molecules. Whereas the PDMSP, the permeability is governed by the solubility rather than diffusivity. Okay? The glass polymers behaves very similar to this because the solubility is not governing the permeability, but permeability is governed by the diffusivity. Okay? So diffusivity controlled the permeability for the glass polymer, whereas solubility controlled the permeability for rubbery polymers like a PDMSP. If you take a look at if you plot the solubility versus the critical temperature of the gas molecules, there is always a linear relationship between the critical temperature versus the solubility of both glassy and rubbery polymers in this case. And the diffusion coefficient is not. Diffusion coefficient it follows always the linear relationship, of course the logarithmic linear relationship between the volume of the critical volume of the polymers for both rubbery polymers and glass polymers. So usually the gas molecules penetrate through those glass polymers, and when we look at the mechanism of the penetrant diffusion in the polymers, you need to know about the diffusion behaviors. Well, in terms of diffusion itself, there might be some course about the diffusion in polymers, okay? And could be a one semester subject. Okay? For example, if you have a bottle of Coca-Cola, okay, your cola is filled with the CO2 gas. Okay? When you open the opener, then your CO2 will be evolved, of course. But if you just close those, the bottom or the cork, and store them, Coca-Cola or Pepsi-Cola, I'm sorry, I'm recording right now, cola for several months, okay? Then the CO2 might be diffused through those PET bottle, right? Because PET itself, polyethylene terephthalate itself, may have a diffusion coefficient. Although it's small, you may have a certain amount of diffusion coefficients. So if you know the diffusion coefficient of materials, then you can estimate when the concentration of those cola bottle made of PET will go down to the level where you do not feel like a cola, right? That's why in many cases, the mart, supermarket will make those cola in sale, right? In a very cheap price, like a $1 or 1,001 from 2,000 or 3,001, right? No, the reason why they are in sale is because the storage time will be close to the level where this diffusion will be much more faster. So diffusion behavior is very important as well. But anyway, we need to know about the diffusion behavior of the penetrants in the polymers in this case. Well, this is the rate limiting step where you create the gaps between the polymer matrix and the local scale of the polymers. What it is that you may have cavities or pores or free volumes. So this white area is a free volume. And assuming that you may have a gas molecule filled with this cavities or pores, and after some time, or after pressurizing those films, okay, and after some time, you may have increased in movement of those penetrants from here to here because of the evolution of those cavities. Now, this is the jump, what we call this jump of those gas molecules. And you can take a look at this physical chemistry textbook about the diffusion, right? So that you can, the earrings, if you look at the earrings, the diffusion theory, in the diffusion coefficient definition, you may include those jump length, okay? Jump lengths from here to here, and the kinetic diameter of the molecules, and the kinetic constants and stuff like that, so that you can calculate the diffusion coefficients. So diffusion behavior is the one that your gas molecules or penetrants will be moving from one place to the other place by time or by pressure or by temperature or whatever the driving force that you get in. So there is just like a vowel, just like our body, one stuff is moving, okay, like a vowels. This is the basic concept of the diffusion of the penetrants in the polymer systems. So you can analyze these diffusion behaviors in equations and so on. And also, just like this, the diffusion behaviors, you're existing with this the polymer filled polymer with the penetrants in one hole, and this hole, because maybe this chain is a polymer chain, this polymer chain is moving. So once you pressurize them, this polymer chain is not fixed, but it's moving, so that you open those hole and rearrange them to become like a jump from one place to the other. So this way you can move those penetrants from the surface to the other surface. So you have the penetrant filling and activation and jump for the diffusion behaviors. You can analyze those polymer molecular motions just like a crankshaft motion in the polyolefins. Okay? In other words, you are moving those polymeric structure from this place to the other place, and it's like a crank structure. It's moving and so on. Right? In the case of polyphenol oxide, they can do the molecular simulation using the Monte Carlo simulation or auxiliary molecular simulation packages, and it's been known for the last 20 years that the distance, as you increase the time of your simulation, then there is a jump length or distance, moving the distance from here to here, and so on. For the oxygens and for the nitrogens, it takes much more longer time for the large molecules, whereas it takes us a short time, and the distance is larger than the nitrogen for the smaller gases such as oxygens. So by using the molecular simulation, you can easily find out that small gas molecules will go faster, whereas large molecules will not be able to. In the case of polyphenol oxide as an example. So by using this concept, you can measure the diffusivity of the oxygen molecules and the diffusivity selectivities of the oxygen over the nitrogen for the known polymers. And if you take a look at this, diffusivity selectivities of the polymers are almost the same, whereas the diffusion coefficient is not. Okay? Diffusion coefficient for the polymers are in some cases larger, in some cases smaller. If you take a look at these polymers, you have a polycarbonate, polysulfones, polyphenol oxide, and polyphenol and sulfides. All of these polymers are glassy polymers, and for the glassy polymers, diffusion selectivity is not a big issue, but the diffusivity itself, diffusion coefficient itself is very important. Okay? So diffusion, this is the diffusion controlled the polymers. If you take a look at the rubbery polymers like butyl rubber and the low density polyethylene, the other rubbers, diffusion coefficient is very large, and diffusivity selectivity is much smaller. So diffusivity selectivity is much higher for the glassy polymers than the rubbery polymers. That's why the diffusivity selectivity is overruling the solubility selectivities, if you look at the selectivities in this case. So the diffusivity was governed by many of the variables. The variable that you can take a look at it is free volume. Free volume was the empty spaces or void spaces. So free volume is controlling the diffusivity. And the stiffness of the polymers. Stiffness of the polymers will give you some void volumes between the rods. Okay, if you have a flexible chain, the chain packing is very compact. Whereas if you have a rigid chain, you may have a very empty spaces between those rigid chains. And this will make the diffusion faster. Polarity will affect this diffusivity. Polymer morphologies like crystallinity and liquid crystallinity will reduce the diffusion coefficients. Size of the penetrants, bigger size, will go slower, will give you the lower diffusivity. And the shape is very important as well, because we assume that we have a spherical shape of the penetrants, but in some cases you may have hexagonal, or you may have slit size, slit shapes, the penetrants, and so on. And so that the size of as well as the shape of the penetrants are very important. Concentration, of course, and the temperature is another factors. So usually, free volume affects the permeability, and higher the free volume, fraction free volume, then you see the lower this 1 over FFV. Okay? This is the reversal of the fraction free volume. So higher the free volumes, you increase your permeability in this case. Okay? Almost a linear relationship between the fraction free volume reverse to the fraction-free volume to the permeability in this case. This is the same for the glassy polymers and the rubbery polymers. The glassy polymers in particular. You can correlate this with the diffusion coefficients with the fraction-free volumes in many cases. Now, if we define the friction-free volumes, okay, this friction-free volume can be calculated. Okay? You can calculate this friction-free volume by knowing the specific volume with the so-called occupied volumes, okay, of the polymer, of the penetrance of the polymer matrices, and the V0, usually the occupied volume is by experience, it's about 1.3 times the van der Waals volume of the polymers. Now you can calculate the van der Waals volume of the polymers from the group contribution method. And if you multiply this by 1.3, then you can get the occupied volume. So that if you put those occupied volume and knowing the specific volume by knowing the density of your density of the polymers, then you can calculate the friction-free volumes. Okay? So next page, I think we will be able to give you how we can calculate this VW. You know, because you know the friction-free volume, then you can calculate the diffusion coefficient as well by knowing the density and the van der Waals volumes. Van der Waals volume can be calculated, as I mentioned, if you know the exact chemical structure of the polymers. So, for example, let's take a look at the polysulfones. Polysulfone has a repeating units like this. So we have 2 ether groups. We have 4 aromatic rings. We have 1 hexa. We have 1 isopropylidine units. We have 1 sulfone groups, and so on. So if you take a look at the Van Cleverin's properties of polymer textbook, then you will know what is the contribution. What is the contribution of aromatic ring to the van der Waals volume? What is the contribution of the sulfones to the van der Waals volumes and stuff like that? So VW can be, because you have 4 aromatic rings, the aromatic ring contributes about 43.3 cubic centimeter per mole, right? Cubic centimeter per mole. So you multiply this by 4 because you have 1 perhaps isopropylidine units, you have 2 ether groups, you have 1 sulfone groups, stuff like that, and these values are tabulated in the Van Cleverin's textbook. Okay? I didn't bring those textbooks, but I think I will perhaps, so that you can calculate the van der Waals volume by these group contributions. So if you know the exact chemical structure of the repeating units of your polymer, then you can calculate even density, van der Waals volume, glass transition temperature, almost every properties from these group contributions. This Van Cleverin is a German, the Dutch, the polymer scientist, and he collected all the information. He collected all the information about the polymers and the properties, and he analyzed what are the contribution of each group. Okay? So if you take a look at those the group contribution tables, you can calculate this van der Waals volume and other properties, of course. So you get about 235.2 cubic centimeter per mole, and this could be converted into the grams by knowing the density, so that this will be the VW in terms of the molar basis, mass basis, will be about 0.53. So the mass base times 1.3, so that the occupied volume will be 0.69, cubic centimeter per gram. Because you know the density, 1.24, so that specific volume will be 0.80. So fraction-free volume is V minus V0, V minus V0 divided by V. So it will be about 0.143. Okay? This means that you have about 14.3% of the volume, of the specific volume, is by empty spaces. So fraction-free volume of 14.3% means that this is very typical. 13%, 14% is very typical for glassy polymers. This way, you can calculate the fraction-free volumes and other properties. You can even estimate the glass transition temperature from the group contribution methods. I think I will give you some, homework to you later on from this group contribution methods. So, this is the list of the tables for fraction-free volumes of the known polymers. If you take a look at the microporous carbons, have very high fraction-free volumes. PTMSP, PIM, TL polymers, other the polymers like this. Okay, most of the polymers like polysulfones or poly-PET, they have about around 14% of the empty spaces, fraction-free volumes, where the PIM polymer and TL polymer has almost double the fraction-free volume of the conventional polymers. That's why we expect that these polymers may have a high diffusion coefficient and permeabilities, right? Permeability was plotted with the glass transition temperatures, and you may have some relationships between TG and the permeability because TG may have different the free volume, the coefficients and so on, but it's a little bit more scattered, right? It's not directly correlated with the permeability, just like a fraction-free volumes, but you may have some range of the permeabilities in this case. We can plot the polarity of the polymers. Polarity of polymers can be changed by adding the second component in your copolymerization system. In this case, we add the acrylonitrile in the butadiene. So by changing the polarity, your diffusion coefficient might be decreasing in all gases that we have tested. Okay? Permeability changes, diffusivity changes in this case. Diffusivity change is not as great as permeability changes in the rubbery copolymers because the solubility may be contributing a lot rather than the diffusivities in this case. So the solubility was governed by the crystallinity as well. Usually the penetrant gas molecules are much more soluble, not in crystalline portion, but in the rubbery portions. So the portion of the rubbery region is really governing the amorphous portion is governing the whole total solubility. So the total solubility is equal to the portion of the amorphous region and the solubility of the amorphous region rather than crystalline regions. And that's reasonable. And the diffusivity is governed by, of course, diffusivity of the amorphous portion and the portion of the amorphous region, roughly in this case. So the permeability is therefore S times D, so that SA times DA is PA, right? And you can multiply this by 2 because we have two portions. So how many, the amorphous region that you have will control the overall permeability in this case. Polymer crystallinity affects the sorption and permeation. And the sorption, in this case, for the polyethylene at 25 degrees C, the friction-free volume, as you increase the friction-free volumes, your solubility increases, much higher for the oxygen than the nitrogen. And argon is larger than the oxygen. Still, this inert gas, if you compare the size of these molecules, the larger size molecule will have a higher solubility than the smaller gas molecules. And so on. In the case of polyethylene, the high solubility material will give you the high permeability and at a given friction-free volumes of the polymers. So the solubility is governing rather than the size of these molecules for the crystalline materials in this case as well. Cross-linking affects the diffusivity and the permeability. So in the rubber, as you add more sulfur contents, the sulfur will be acting as a cross-linker. So high sulfur content means the high cross-linking density. So if you cross-link the further, diffusivity drops as well as the permeability. So the cross-linking always affects the lower permeability due to the reduction of the diffusivity. Size of the gas molecule is also important. The oxygen is smaller than nitrogen. So the smaller gas molecule give you a high diffusion coefficient and little higher solubility in this case, so that you contribute this to the permeability, and the permeability is about 6 times higher, whereas the diffusivity is about 4 times, and the solubility is about less than 2 times. So the main contribution is due to the diffusivity to the permeability in this case for polyethylene, polysulfones. So permeability selectivity is about 5.6, diffusivity selectivity is 3.6, solubility selectivity is 1.6. So for glassy polymers, solubility selectivity is quite low in many cases, whereas the diffusivity selectivity is a little higher than solubility selectivities. This is the same figure that I have shown you. Glassy polymer has a lower diffusion coefficient as you increase the size of the gas molecules, whereas the rubbery polymers are usually increasing or higher than the glass polymers. CO2 is smaller than methane. Therefore, diffusivity selectivity of CO2 over methane is higher than the solubility selectivities. Note that in this case, the polysulfone solubility selectivity is much higher than the polyethylene cases. Okay? Therefore, although the permeability selectivity is about the same, solubility selectivity was increasing, which is not the same case with the polyethylene. Concentration of the gas molecule may have affect the diffusivity, but as you can see here, it's relatively small in this case, but as you increase the concentration, your diffusivity will increase, in fact. So diffusivity itself is not independent on the concentration of the penetrants, but in fact, diffusivity will be the function of concentrations. Okay? Particularly in the case of very highly absorbing penetrants. Okay? If you are using liquids, this is much more severe, whereas the concentration dependence of diffusivity much smaller in the case of inert gases. Okay? But if you have highly soluble gases, gas molecules, or even the liquids or vapors, concentration dependence is much more severe. Right. In the case of the higher hydrocarbons or organics, you see concentration dependence, which is much more severe in the case of diffusion. Okay? So diffusion with the polyethylene oxide for hydrocarbons, concentration dependent, and the water in ethyl cellulose is in reverse positions, and others. So concentration dependence of diffusion coefficient in the case of polycarbonate with the CO2 is increasing, sometimes decreasing for the water and polyethylenes. So it's actually its diffusion coefficient is not independent, but it's dependent on the concentration of the penetrants. So in summary, we have seen the diffusion aspect of the gas molecules, and the diffusion coefficient, in fact, is a function of the concentrations, and you should be very careful that diffusion coefficient is not just a constant, okay? Even in the gas molecules, particularly in the condensable gases like CO2 and methane. You have to be very careful about the interpretation of your data of the penetration and permeability with the diffusivities. Now, in the case of the dissolution, gas dissolution, which is a solubility, we need to know more about the gas molecules in the liquid form. And also in the if you are using the gas mixtures. Okay? If you are using the liquid molecules, we have to be very careful about the condensation of the gases, particularly the condensable gases. Condensation occurs at the surface of the interface between the gas molecules and the polymer molecules. So the condensation of the gas molecule is important. Mixing of the condensed gas with the polymer molecules, even inside the polymer, is also an issue. So the first step is about the condensation energy. Is often the dominant contribution to the total energy required for the gas solutions. So we need to know about the condensability of the molecules in terms of the critical temperature of the gas and the boiling point of the gas molecules. So we'll take a look at it. And solubility usually is a function of the critical temperatures, as you have already seen in many gas molecules. So the solubility for both the glassy polymers and rubbery polymers are a function of the critical temperature of the gas molecules with this type of equations for both of the polymers. And although the slope is the same, the intercept is a little different. Okay? Now B, which is a slope, is about the same for most of the gas molecules for the solvents and the polymers. The solvents, the B constant, and the polymers, B constant for the polymers are about the same. So you see those trends with the same polymers. If you just change the polar groups, the acetonitrile in liquid solvent with the CO2 solubility versus the critical temperature, then there's something happening. Okay, so by changing the polarity, then solubility will be much more affected as well. But if you're using just a normal polymer molecules, just a typical polymers, then this is just a function. But by changing the solubility parameter, by changing the solubility parameter, you will change the solubility of the CO2 in this gas. Polar group in the polymers on the solubility and the CO2 nitrogen selectivity is listed here, where if you change the solubility parameters, the solubility is about the same for most of the polymers, although there are some scatter. But the selectivities are about the same as well. So by changing the solubility parameter in the polymers, your solubility of the most of the polymers are about the same in this case. As you have already seen, the critical temperature will affect the solubility in the logarithmic scale, and you see for some gases like the ethane or the hexafluoroethane, you have a linear relationship between the concentration with the pressure, so it follows the Henle's sorption behaviors of the polymers, and that means that you may have in some cases the gas sorption interaction between the polymers that may not be favorable to the total the separation efficiencies. You have a little different behaviors in this case. As you increase the temperature, it follows, initially it follows the Henle sorption, but it behaves like a the Flory-Higgins sorption behaviors in some cases. If you are using the PDMS, polysilicon rubber with the propene. Okay? So propene will dissolve this PDMSP as you increase further on the concentration. So this curve behaves like a Flory-Higgins model, and in this case, the solubility is a function of the concentration of the penetrants divided by the partial pressure in this case. So solubility is not just a function of the concentration itself, but solubility is mainly governed by the critical temperature of the gas molecules. But if you for most of the polymers, in some cases, it follows the. So if you apply the pressure, then pressure is really affecting a lot to the solubility as well as the temperatures. It follows like in some cases follows like this behavior. It's again, this is different from what we have seen in the previous slides. Okay, the concentration versus the pressure, and in this case the polymer is a polysulfone. If you are taking the glassy polymers, then usually it follows the dual mode sorption behavior. Dual mode sorption behavior is the one that we have analyzed with the Langmuir sorption and the Henle's mode. So the glassy polymers always follows the dual mode sorption model, whereas the rubbery polymers are following, in many cases, the solubility model, such as Flory-Higgins models. This is the dual mode sorption behaviors. As you increase the temperature, then the CO2 sorption is much intensive for the PET cases in this case. So far we have seen a lot of those glassy polymers and bubble polymers and sorption behaviors and diffusion behaviors for gas molecules. And typical polymer that has been used for the last 3 decades are polysulfones. Polysulfones are very typical polymer, and this typical polymer could be utilized as a first commercial gas membrane produced first by Monsanto, but later by Air Products from 1990. And polysulfone has a relatively good gas pair selectivities, and it's commercially available, of course. The polymer is commercially available. That's very important. And mechanically very nice. And this was first studied by Professor Koros and Professor Paul. And Koros was first PhD student of Dr. Paul. And Dr. Paul was graded over in North Carolina State as undergraduate student. And he did his PhD at Wisconsin, and he became the professor at the UT Austin back in 1970s. And Bill Koros was the first PhD student, and he did dual mode sorption analysis of PET in gas molecules, okay, with different temperature and pressure, and he got this dual mode sorption curve, and he analyzed those capacities and stuff like that, and then he can change these polymers from polysulfone to other polymers, other glassy polymers, and he found the same behavior but with a different B prime and CH prime and stuff like that. And they collected all the data, and Bill became an assistant professor at North Carolina State in 1977. But he moved back to Austin in 1983 and became an associate professor working together. After 20 years, Bill moved to Georgia Tech right now. Okay. And Benny Freeman is replacing Bill. Okay, the polysulfone is a back. You have ether groups and polysulfone groups. We have 4 aromatic rings. But if you substitute these groups and compare that with the permeability and selectivities, you may have a little bit of different different values. If you take a look at this polysulfone, glass transition temperature is lower than the tetra-substituted ones, because if you substituted this, okay, the rotation is limited because of the static hindrance. Okay? Therefore, the glass transition temperature is higher for tetramethyl substituted polysulfone than non-substituted ones. Permeability is pretty high, about 4 times higher than for substituted ones than non-substituted ones. Permeability selectivity is about the same. Permeability of oxygen is of course about 4 times higher, and the selectivity is about the same. Okay, so you can take a look at what's going on. So the substitution may have affected the solubility selectivity in this case. If you further substituted those with the trimethylsilyl group in one place, okay, and compare them, the permeability increases as you substitute further. Much bulkier group, like a trimethylsilyl group, will contribute to the high permeability for both CO2, oxygen, and nitrogen, and methane. But the selectivity may, maybe reduced a little bit, about 10% decrease. But the contribution to the increase in permeability is great, about 20 times. Selectivity decrease about 10% decrease in all cases. So this is quite interesting data, and substitution effect. Substitution of the polymer will affect the gas transport properties. If you have a little bulkier group, then it's the same thing. You increase your permeability, but a little bit decrease your selectivities in many cases. So when you have a backbone polymer with a little bit of a substitution, you will make the steric hindrance. You restrict your rotation of your backbones. That will increase the fraction-free volumes because of the rigidity, okay, which is the item that I have already mentioned to you. That way you can increase the permeability while maintaining the selectivities. So in summary, substitution of the methyl group, or substitution of the tetramethyl group, or substitution of the trimethylsilyl group will contribute to the permeability. And due to the increase in fraction-free volumes, due to the increase in the despacing, this spacing can be detected by the wide-angle X-ray, right? Wide-angle X-ray. Whereas fraction-free volume can be calculated and measured so that you can analyze those increase in the permeability with those parameters. Okay? And if you measure the glass transition temperature, high TG material will give you high fraction-free volumes. Therefore, you can expect to have a high, the permeability because of the rigidity in your cases. Usually, aromatic ring gives you much higher the chain packing. Higher the TG. Therefore, you expect to have a higher permeability in many cases, rather than aliphatic containing polymer. This is the connector contribution, connectors, okay? So we have a polysulfone. We have polysulfone with the 6F group. So if you replace this methyl group with hexafluoro groups from hydrogen to fluorine, fluorine is much larger than hydrogen. Therefore, you contribute to increase in the glass transition temperature. If you increase the glass transition temperature, again, you expect to increase your permeability. Selectivity is about the same, increase the permeability for oxygen and so on. If you have an ether group, if you compare with the polysulfone and the ether group will decrease the TG, you decrease the permeability in all cases. If you replace this isopropyl group with the methylene, you further decrease the TG, further decrease your permeability, stuff like that. Sulfone will contribute to the polarity, so they increase the glass transition temperature, but decrease the permeability, but increase the selectivities in this case. Bromination, however, this is the polyether sulfone rather than just the polysulfone. So ether group is replaced by the sulfones in this case. If you brominate them, then the TG is about the same, but bromination in the substitution sites will contribute to increase in the permeability in many cases. Okay. So by manipulating those substitution strategy, as well as by just changing the monomer strategy, you can manipulate those permeabilities, although it's not that great. 6F group, again, in many cases, it increased the permeability. Okay. 6F group increases the chain stiffness, inhibits the interchain packing, therefore increase the permeability in many cases. So if you contain the 6F group in the monomer, you increase the permeabilities. However, 6F group containing monomer is very expensive. So you have to be very careful in this case. Ether group is a swivel group. So as I mentioned to you, the ether group will decrease the permeability in this case. Sulfone is much more polar. And so I think you can manipulate those strategies. Diphenyl. So if you have two phenyl groups in one sulfone, it's like arranged to the right angle. So the conformation will give you the conjugation interaction between the phenyl group, 5-5 interactions, with the sulfur group. Therefore, it makes phenyl sulfone with very rigid group, just like this, so that you increase the permeability in many cases. Whereas if you have a polycarbonate, this is the commercial polymer. The commercial polymer by PPO by General Electric, Lexan polymer, with very good transfer properties for many of the polymers. Again, if you have a substitution, you increase the, if you have a tetramethyl substitution, you increase the permeability, so that if you make the bromination, then bromination will lower the, in this case, lower the permeability, but increase the selectivity, okay? In oxygen and nitrogen cases. Although it's not that great, you can interpret those data in terms of the spacing, dispacing, glass transition temperature, rigidity, stiffness, flexibility, stuff like that. So polycarbonate, you have a chlorine substitution and a bromine substitution. And chlorine substitution will increase the selectivity while maintaining the permeability. By changing just the substituent groups, you further increase the selectivities. TG is different. TG starts from 150 to about 260. So TG is not the only the thing that you can take a look at it, but if you compare this PC with the TCl PC and TBr PC, then we can take a look at the increase of the permeability. Whereas methyl units will increase the permeability by increasing the TG in this case as well. Polyimides are another commercially available polymer. We have at least two types of the polymers, matrimide and ultam. And those polymers have a typical imide structure, and this is commercially available. But you can make the polyimide in large scale without any problems. Polyimide requires the dianhydride as one component of the monomer, and the other one is the diamines. Okay? So by combining those dianhydrides and diamine, you can make a polyamic acid and polyimide later on. I think it was described here, but imide could be polymerized by adding the anhydride and monomer diamine in the reactor in the presence of a solvent such as NMP, and at a low temperature such as about 50 to about 70 degrees C, or room temperature even, then you can open those rings by attacking those nucleophile to the carbonyl and make the amide acid. So we call this as a polyamic acid precursor, and this is soluble in the solvents at low temperature. And the viscosity increases, of course, as we proceed to polyamic acid. If you increase the temperature above this 100 degrees C to, in many cases, even up to about 300 degrees C, as low as 200 degrees C, then you can have ring closure reactions. Okay? This nitrogen will attack this carbonyl, and ring closure reaction will be formed. And so you have a ring closure by removing this hydroxyl and hydrogen as a water molecule. So the water is a byproduct. So you have to add the plus water in this case. So you need to add the agent to remove those water out, and you need to pull the vacuum in order for the condensation reaction to proceed to make this polyimide. Okay? So typically, there are at least 4 or 5 methods to make this polyimide. You can, a very simple reaction is that you make this polyamic acid and cast a film, cast a solution on the top of the glass plate, and then put it into the oven and increase the temperature in the stepwise reaction, then make the polyimide. Okay? But that's called the thermal imidization method. Or you can put this amic acid and pull the vacuum and get the water by adding the azeotropic agents such as xylenes and increase the temperature up to 180 degrees C. Then you can have a powder. You can have and after precipitation, then you can get the powder of the polyimide. Or you can add the acetic acid to make this acetylization of this carboxylic acid, and later on you can remove those acetic acid in the second step, so that you can have what we call the acetyl. I think I forgot the name. Acetylization, imidization, stuff like that. And also, another method is called the acid method, and you can make this polyimide as well as a soluble precursor. By changing the monomer in dianhydride and diamine, by combination of all those monomers, you have different types of polyimides. Okay? So there are too many types of polyimides that was published in the literature. Again, if you have a bulky, if you have a larger, the monomer rather than smaller in size of the monomer, then you have a higher permeability by using this 6F group as a precursor. So by combining this 6F and 6F in both anhydrides and diamine, I think you have the maximum permeability, but you can expect some problems. If you have an ether group, again, you have a very good compaction, so that permeability is expected to be low. If you have a none or smaller, only one aromatic group, you expect to have a very compact system, so that permeability will be quite low in this case as well. So polyimide, you have a pretty the reasonable glass transition temperature. We have a large number of pairs of the polymers, and again, we expect to have a very. I think this is the same slide. Right? So in general, we can improve the permeability and selectivity in the glass polymers by adding the chain stiffness by adding the bulky substituent groups or poor packing, so the increase in the despacing, and the interaction between the chain should be lower, right? If the interaction between the chain is quite high, then the chain packing is much higher, so that you expect to have a lower permeability in many cases. If you are using naphthalene units in 6F group, there are also interesting structural features. In this case, you can increase the permeability by adding 6F group and by adding naphthalene units in this case. TG is increasing because of the 6F group and because of the naphthalene units in this case. So you reduce the mobility by adding naphthalene units rather than benzene units or phenyl units. This compares the permeability. If you have an ether group, ODA, you have 2.7 in CO2 permeability with high selectivity, but if you replace this with the isopropyl units and 6F units, you increase the permeability, but lower the selectivities. Okay? But if you compare this first and third one by adding the biphenyl units rather than just the phenyl units, you further decrease these units. This is because you have although it's rigid, it's very flat, but the spacing between the biphenyl and the phenyl groups might be different. Okay? Might be much smaller in these biphenyl units, so that the permeability will decrease, whereas selectivity will increase in this case. So there is a lot of other things, 6F and ODA. You can compare that, and you can study about the structure and property relationship of the polymers, particularly in the polyimides, with the permeability and diffusivities. With the same ODA, you can change the anhydrides, and 6F group, of course, will give you high permeability because of the bulkier group in this case. Okay, I think I need to stop about right now. And I think we have talked about the structure and property relationship, as well as diffusion and the solubility of the gas molecules, gas penetrants in the polymers. Any questions so far?